Assalamualaikum warahmatullahi wabarakatuh. So in this video I'm going to illustrate another example of rates of change in the medical area. Suppose the interest is to study the flow of blood through a blood vessel such as vein or artery, and the shape of artery or vein here can be considered as a cylindrical tube, which is illustrated by this figure here, with radius r and length l. So let me just represent it properly. So this is the length of the tube, so this could be represented by l, and then the tube here has the radius is measured from the center point here towards the outer, towards the wall here, so that will be big R. That is the radius and the length. Next, due to friction at the walls of the tube, the velocity of the blood V is the greatest along the central axis of the tube. So this is the central axis, and therefore the velocity of the blood here is the greatest, and the velocity here decreases as the distance from the central axis increases. So the distance from central axis towards the outer part here is denoted by small r. Okay, so in this one we can represent this. Okay, so this is small r, so it represents the distance from the central axis towards the wall. So this is small r. Okay, there is a difference between small r and big R, and eventually when r is the same as r, when the length of r here is the same as the radius, the velocity here will become 0 at the wall. Now the relationship between velocity of the blood and this distance from the central axis is known as the law of laminar flow, and it is discovered by a French scientist. Okay, so Jean-Louis Marie Poiseuille in 1840. Now if you look at this mathematical notation here, delta V over delta R, it represents the average rate of change of velocity, because delta V here is the change of velocity with respect to radius. So this is the distance from the central axis. Now if you add another term, add a term of limit delta R approaches 0 to delta V over delta R, then this expression here becomes the derivative, and it is also known as the velocity gradient. Okay, let's look at this example here. Consider a blood vessel with radius 0.01 centimeter, length 3 centimeter, pressure difference between the ends of the tube 3000, and viscosity of the blood 0.027. Now using the law of laminar flow, so this is laminar flow describes the velocity of the blood. Find the velocity of the blood along the center line where r is 0. R, the small r here, is the distance from the central axis, r 0.005, so the distance increases, and at the wall the distance gets even further, so r 0.01. So in order to answer question A, what you need to do is you just need to substitute these values here into this law of laminar flow. Okay, so that's what I'm going to do. So I'm going to write down the equation. So this is the velocity, is given by P. P is a pressure, so I'm going to substitute 3000 over 4. Viscosity is 0.027. The length is 3 centimeter. The big R is the radius of the blood vessel, which is 0.01 squared, and we have the small r. Okay, so this is the, I'm just putting down all the constants, okay, all the information given. So now this can be simplified as, which one? This can be cancelled. 1000 over 4 is 250, so that can be simplified as 250 over 0.027, 0.01 squared minus r squared. So now when r is equal to 0, therefore the velocity will be 250 over 0.027, 0.01 squared minus 0 squared. So this will be about 0.9256. So this is the velocity of the blood. Okay, next, when r is 0.005, v will be 250. Okay, we're just repeating the same procedure over 0.027, 0.01 squared minus 0.005 squared, and then you will get that the answer is 0.6944. Now when r is equal to 0.01, which is the same value as the radius, clearly if you substitute the values there, it will be 250 over 0.027, 0.01 squared minus 0.01 squared. So this one here will become 0, therefore the velocity will be 0 when r is 0.01. So I hope you can see that based on the answers that we got over here, the velocity decreases from 0.9 at the central axis to 0.6944, and it becomes 0 at the wall. Okay, right. Next, find velocity gradient at r equals to 0. So now find the velocity gradient at r0, 0.005, 0.01. So velocity gradient is basically you need to differentiate this function here with respect to small r. Okay, right. So I'm going to erase this slide, and we're going to focus on answering the second question. Okay, this takes a long time. All right, next. Okay, second question. Find velocity gradient. So now I'm going to write down again. The equation is 3000 over 4, 0.027 times 3, and then I have 0.01 squared minus r squared. So I'm just considering all the information, putting down all the information into the equation, and this one I can actually cancel out, so that will be 1250 over 0.027, 0.01 squared minus r squared. So now I'm going to differentiate this function. So dv dr will be equal to, this is a constant, so I'm going to put it aside. I'm sorry, 0.027, 0.027. Now if I differentiate this part here, this will be also a constant, so this will be 0, and if I differentiate this one, I will get -2 times r. And so this can be simplified as negative 500 over 0.027 r. Now the fact that we get a negative sign here, it means that the velocity will be decreasing over time. Okay, it will be decreasing as the radius changes, and based on this, based on the result that you got here, we can find the velocity gradient at r equals to 0, r equals to 0.005, and r equals to 0.01. Okay, now we're just going to substitute the value. So when r is equal to 0, dv dr is just 0. Okay, negative 500, 0, 0.027. So the answer is 0. When r is equal to 0.005, dv dr is negative 500, 0.005 over 0.027, and the answer here is negative 95.5926. And when, okay, I'm going to write down here. So when r is 0.01, dv dr is just negative 500, 0.027 times 0.01, and the answer here is negative 185.1852. So to answer question C, where is the velocity the greatest? This one, the velocity is the greatest when r is 0. At r is 0, that means at the central axis. So greatest at central axis. Where is the velocity changing most? So the velocity is changing most at r equals to 0.01, because based on the answer here, the slope is the most steep, which is negative 185.1852. So at this place, okay, this is where the velocity is changing most. All right, there are of course many other examples out there. For example, in physics itself, there are other rates of change of interest, such as density or power, rate of decay of radioactive substance, for example. And in chemistry, maybe you want to study the rate of reaction. In biology, for example, in the study of animal or plant population, you may want to see what's the change of population size between the times t equals t1 and t equals t2, and therefore the average rate of growth is given by this function. Now, if you want to find the instantaneous rate of growth, of course, in what you have seen before this, you just need to add the term limit delta t approaches 0, and so you will get the instantaneous rate of growth. Now, interestingly, all the above are special cases of single mathematical concept, which is the derivative. All right, with that, thank you very much, and hope that this has been beneficial for you. Thank you for watching.